Welcome back to a Mr. Hutton Science chemistry lesson. This is Rates of Reaction lesson 3, and this is all about surface area. These lessons, as always, they relate to the AQA specification. So the specification links for this particular lesson are there in front of you. If you are from another exam board, then the lesson will be useful, but you just need to double check with your own specification that everything you need to know has been covered in this lesson. So students at my school, these are the resources that we have available to us and the page numbers for the books that we'd be using. Some of you may have some of these tasks to do alongside this video. Right, as always, I'd like to start the lesson with a few pictures and see if we can work out the lesson title from those pictures. Because you're on the video version, you've already been told what the lesson title is, but see if you can link these pictures to that lesson title. This one's a fairly easy one, so have a go now. Good. So hopefully you've linked all of those pictures. It is quite straightforward, this one. So the Sir David Attenborough there, so Sir, and then there's a face. So Sir and face. And then at the bottom we've got some Nike Air trainers, and then there's a rhea bird. Okay, so when we say those quickly together, surface area. All right, so that's today's lesson, surface area. There we go. Again, this is from the AQA specification. I won't dwell on it too much, but the key points there at the bottom, students should be able to recall how changing these factors affects the rate of chemical reactions. And the factor we're looking at today is the surface area of solid reactants. Lesson objectives and outcomes. If you want to pause the video just to look what things you need to know for different grades, then do that now. Alright, so let's start. We've got two pictures here, a sugar cube and a teaspoon of sugar, and the question says, which sugar option will dissolve quicker? Another point to make is there's 2 grams of each, so the mass of the sugar is the same. So just think now, which one will dissolve quicker? Okay, well hopefully you've said the teaspoon. Okay, even though there's the same mass of sugar in each, they both have 2 grams, the teaspoon has a much larger surface area. So the sugar cube is like one big block, whereas the teaspoon of sugar, they're all tiny individual particles, and they can all be exposed to the tea itself to dissolve in, whereas the sugar cube, only those particles on the outside of the cube will be exposed to the tea. So thinking back to that example of the sugar cube and the teaspoon of sugar, how could we increase the surface area of this 5 kilogram rock, this basalt rock? How could we increase the surface area? Have a think about how we could do it. Good, hopefully you came up with the idea of chopping it up into smaller pieces. At the top left there we've got 6mm chips, then we've got 8mm chips, 12mm chips and 16mm chips, and hopefully those pictures will show you how the size of those particles have got slightly bigger going from the top to the bottom corners. So what you'll notice as well is that they all have 5 kilograms. We haven't changed the mass. Okay, we cannot change how much of it we have. All we've done is break it up into smaller pieces to expose more of it. In that central picture there, the big rock, only those outside surfaces are exposed. So only those outside surfaces can react with something else. When we break it up into smaller pieces, the 6mm chips, all of the outside surfaces of every single 6mm chip is able to react. So we've exposed a much bigger surface area. Right, looking at these again, at the top there it says what happens to the total number of particles, or effectively the volume of what we've got, or the mass in this case. If there were 6 billion particles in our original basalt rock, how many particles will there be in each set of chips? Have a think about that and come up with your answer. Well, hopefully you've said 6 billion. Even though we've broken it up into smaller pieces, the number of particles has stayed the same. That hasn't changed at all. All we've done is expose more of them, so we've increased that surface area. This links into maths now, and how we'd calculate surface area and volume. This is something hopefully you should be aware of already. It's one of the common kind of things that you'd have to do in maths, and you use it in all sorts of subjects as well. But just to remind you, surface area, okay, the example we've got there of a cube, so it's going to be the height times the length of that face, so A times A. And then because there's 6 faces to the cube, okay, we times it by 6. So we've got A times 6. So in this particular example where A equals 8, we've got 8 times 6, which is 384 millimeters squared. Okay, so surface area is measured in millimeters squared, or whatever units you have squared. So it could be centimeters, it could be meters. The volume of a cube, height times length times width. So it's 8 times 8 times 8, which is 512 millimeters cubed. Okay, so for volume, it's in cubed. So if you remember back to the first lesson when we were measuring volumes of gases, that was measured in centimeters cubed. All right, so volume is in cubed units, and surface area is in squared units. Okay, so we've got an example of surface area and volume for that particular cube. So what we're going to do, like we did with our basalt, we're going to break it up into smaller pieces. So this cube has now been broken up into 8 smaller cubes. And you can now see that the value for A on each one of those cubes is now 4. So if we go ahead and calculate the surface area and volume again, you'll see the dramatic difference. Okay, so surface area now that we do 4 times 4 times 6, that will give us the surface area of one of those cubes. Because there's 8 of them, we then times that by 8, and the new surface area that we've got exposed is 768 millimeters squared. The volume, however, has remained the same. So even though we're doing a slightly different calculation, okay, this time 4 times 4 times 4, and then there's 8 of them, so we times it by 8, the total volume remains the same at 512 millimeters cubed. So we haven't changed how much of it we have, but what we have done is we've exposed a much bigger surface area. So just on the right there it says the volume is how much of something you have, and the surface area is essentially how it's arranged, or how much of it is exposed. Right, here's a task for you to do. We've got 4 different diagrams here, and similar to what we just did, you need to calculate the surface area for each one. So if you remember, the surface area is going to be the height times the length, and then times that by 6 for the number of faces that you've got on the cube. Have a go at that now. Pause the video whilst you do it. Okay, you should then, for the first one, have had 5 times 5 times 6, 150 millimeters squared. So remember, this is surface area, so it's in squared units. For the next one, where we've split that up into 8 particles, our individual particle is now 2.5 millimeters. So 2.5 times 2.5 times 6 equals 37.5 for one of those blocks. And then because we've got 8 of them, we times it by 8, which is 300 millimeters squared. Now we've broken it into 64 pieces, each one with 1.25 millimeter sides. So 1.25 times 1.25 times 6 is 9.375. So that's for one of those small cubes. And then there's 64 of them, so we times it by 64 to give us 600 millimeters squared. Finally, we've got 512 tiny little pieces now, and the size of those, the width and the height there is 0.625 times 0.65 times 6 to give you 2.34375 for one little square, one little cube. And because we've got 512 of those, we need to times it by 512. So the mass is the same, the volume that we've got there is the same, but the number of particles and the amount of particles we've got exposed, the surface area, is 8 times higher. So we've gone from the top left down to the bottom right, and it's 8 times higher in terms of the surface area. Right, so this essentially is like our sugar cube and teaspoon scenario. Right, so the one big particle is our sugar cube, and then our teaspoon is where we've broken that up into the many small particles. So this is all linking in again to remember rates of reaction. So how can we make a reaction faster? All right, so what we're looking at here is changing surface area. So in terms of dissolving, in this example, the teaspoon will dissolve quicker than the sugar cube if they're the same mass. Now then, what we need to do is look at the surface area to volume ratio. You've just calculated the surface areas, and we know that the volume is going to be the same on each one. So what you've got to do quickly now is just calculate the volume of one of these, and that will be the same for each one. So for example, I would take the top left one, that would be your easier one. So remember, volume is height times length times width, and hopefully you'll come up with an answer shortly. Just pause the video to have a go. Good, so hopefully you came up with a volume of 125 millimeters cubed. And here we can see our surface area to volume ratio is 150 to 125. What you could do there, you could actually use that ratio and make the numbers smaller. Okay, so you could divide each side by 5, for example, and then your ratio would be the same, but your numbers would be smaller. Here we've got 300 to 125. So remember, our volume is staying the same. Okay, and then we've got 600 to 125, and then 1200 to 125. So increasing the surface area to volume ratio for any solid reactant will increase the rate of reaction. So if you can expose more particles of a reactant to the other reactant, then you will increase the rate of reaction. So that's why with the sugar cube, by crushing it up into the just a teaspoon, that will increase the speed at which that dissolves. So that's the same for other reactants we use. If we were going to use a lump of calcium carbonate, for example, so a piece of chalk, or we could crush that up into tiny little pieces and use that instead. Okay, and the tiny little pieces, the powder, that would have a much larger surface area to volume ratio than the piece of chalk itself. Right, so let's look at this in terms of a kind of exam question scenario. It says here, describing the effect of increasing surface area. So use the knowledge that you've learnt in previous lessons and from this lesson to determine which line here is for 5 kilograms of powder and which line is for 5 kilograms of 6mm chips. So have a go at doing that now. Alright, hopefully you came up with the steepest line. Remember, the steepest gradient, the fastest rate of reaction is the powder, whereas the less steep line is the 6mm chips. So why are both of these lines plateauing, flattening out at 100 centimeters cubed? Even though the powder one gets there quicker, okay, why do they both level out at 100 centimeters cubed? Just think about that. Look at the question, and you may find a clue in the question there. Pause the video to have a go. Good, the total mass of reactants is the same. So in each case, there was 5 kilograms of powder and then 5 kilograms of 6mm chips. It's the same. So you're going to have the same volume of gas produced. It's just the powder is going to happen quicker than the 6mm chips. Alright, this time we're going to be using our collision theory to explain the shape of the two lines. So whilst we just described what happened, now we need to explain it. We need to give scientific reasons why this has happened. So there's a clue here that rate, remember, rate depends on how frequently the particles collide, okay, and the energy with which the particles collide. Now, with what we've done here in terms of surface area, we haven't affected the amount of energy the particles have. Okay, we haven't done that at all. But what we have done, we've changed the surface area, so we've exposed more particles, and therefore we've affected how frequently particles will be colliding with each other. So see if you can come up with some good answers here for explaining these two graphs. Pause the video to have a go. Well, thanks for watching. The next lesson is following on from this. I think it's temperature, and we'll be having a quick look at how temperature affects rate of reaction. But make sure you're subscribing and sharing with others, and look forward to seeing you next time.